So this talk is going to report on the status of several sub-projects in the general Geo project. So Geo started in 2014, version 10. So it has been quite a few times already that we have been talking about Geo. So there are multiple different sub-projects, as I said, going on. And I'm going to talk about a few of them. So we are continuing improving our vector maps, which soon should be the default of our results in Geo. We have linked to a new version of the Geo library, which is a great library out there for Geo formats. So we are adding new Geo formats, and more of them will be coming in new versions. We are also linking to other libraries for geometric and computations and geo projections. New styles of geo projections based on grid files. We have updated this year our provider of satellite imagery. I will talk about that. And something important is that the Astro project and the Geo project share much functionality internally. And therefore, there has been some aspects of the computation that has been motivated this year more by the Astro project and the Geo project. So the truth is that I have more material to talk about and more fun material to talk about in Astro than in Geo. So something I'm going to do today, I'm going to cheat, and I'm going to move part of the Astro material to this talk at the end of the talk. And so I will go through it more slowly in this talk, and then I will summarize briefly that material at the beginning of the Astro talk for those of people who will be attending next talk only. Okay, so the outline of the talk is to briefly mention progress in vector maps, talk about Geo formats, Geo computation, new satellite imagery, obliqueness, which is one of these aspects motivated by Astro, and this part of the next talk that I was talking about, the reference frame and time systems, something that I started talking about last year. Okay, so in vector maps, we continue improving mostly details, and so don't be surprised if you evaluate a map and then the next day you evaluate the same map and things have changed. And here we have a simple example of that. So for example, here we have the vector maps. You remember that so far, if you want vector maps, you have to opt in. You have to specify in the Geo background one of our 8 vector styles. And so if we compare to our current map, which uses vector labels, you see, for example, how much smaller the font or Urbana is. We have removed shields. Steven, for some reason, doesn't like shields at high zoom levels, or I should say low zoom, high scales level maps. So we are changing all the time these little things, and improving what you see. Okay, so not much more to say on that front. So let's talk about Geo formats. So as I was saying, we are linking to a new version of GDAO. And as an example, I'm going to show an example of a new raster format and a new vector format. So let's start with the vector format. So this is, so you can go to openstreetmap.org and select a region and download a file that by default will come in the format OSM. So this is one of our new vector formats. So I have done that for the region around us. And we can now import this file, and we get that. So notice that all these lines that we see here have been imported. The background is actually added by us. This is our own background, right? But you can now get the primitives and yeah, I mean, you can add any additional things that you have in this format on our maps. So that's one. And then as an example of a raster format, I'm going to show GXF. So this is a format very much used by the scientific community when describing the gravitational and magnetic fields. And this is an example of something called the Bouguer anomaly. The Gauguin anomaly describes the difference between the real gravitational field and what you would expect if the landscape was like superflat. Right? So this anomaly is describing the variations in the gravitational field due to the topography. So you expect that it's going to look like the region around the measurement. And so this is Lake Superior. So again, we are going to import this, this map here. And we can now extract the two main properties we always need about any map, which are the projection and the ranges. So we get the projection and we say, that's clearly UTM zone 16, right? The 16 of the 60 zones of the universal transverse Mercator projection. No? Just to check that we can confirm that. So you have the right center, right scale factor, etc. So now one question that you might ask is, well, in the previous case, we immediately showed the vector primitives on top of a map. How do we put this image on top of a map? So we can do that as follows. So we extract the range, which is this. This is the projected range. This projection works in meters. So these are meters measured horizontally from the meridian -87 and vertically, or I should say south-north, from the equator. So this is millions of meters, thousands of kilometers. Okay, so we create a polygon, a projected polygon, of course. So we have to use geographic position. And we do this. We overlay that image on the map. This should have been transparent, so we will fix that. But you see here how the map, that the relief map underneath is showing the same structure of this map, right? And this is, as I said, this is very impressive. It's the effect of the topography on the gravitational field. Okay, so that's GXF. Geo Computation, there is something that we are starting to do now, which is moving our description of Polygon stuff from Polygon of geoposition to the new GeoPolygon object. And I'm going to show you a function that we will all be using internally to do this. And so if you happen to need this transformation, here you will see the function. So, so this is our current presentation of the world polygon. So until recently, the way in which we had holes in geometry was using field curve. Now we have the new rule notation for polygons with holes. So this is a field curve in which the Eurasia polygon, and with Africa too, has two holes. One is the Caspian Sea, the other one is a water area in the Netherlands. And then the rest of the polygons, like almost 7,000 polygons. Okay, so there is this new internal function that you run it, and it will return the very same thing, but as a geopolygon, right? And now you see it's much easier to manipulate and, well, to see at least, right? Rather than this big thing. And now, of course, this thing can work as well in geographics as the other representation did. And so we see now here the Caspian Sea. Or if we do show the Netherlands, we see this other hole, right? This area here is represented as a hole. So the polygon outside goes to that. Okay, perhaps you don't use much show. Show can redo a geographic map. And what it does essentially is preserving all options except for three: georange, geocenter, and geoprojection. Those three are recomputed. So once I have selected a new area, it will throw away the previous range information, center information, and projection information, and also it will recompute the zoom, right? So you see these are different tiles, and this was eco-rectangular, this is Mercator, right? So show actually calls again geographics. This is an internal tool that we currently have to convert from this notation to that notation, which in the future is what we will get, right? But it will take some time to change everything from using polygon of geoposition to geopolygon. But my point is that if you want to change it now, you can use this. Okay, satellite imagery. So before continuing, I'm going to remind you of how zooms work, because I understand not all of you are so familiar with zoom levels in relation to scales. So there are two ways you can think of zooms. One is the total range of the map. So one would be the whole world, 20,000 kilometers, to 18, which would be a map across like 150 meters. Or you can think it in pixels. And then we just divide by 256, which is the number of pixels per tile. And so we start with 78 kilometers, or we end up at the equator with like 60 centimeters for zoom 18. Okay, so from zooms 1 to 8, we still use the same tiles. These are tiles that we have here, and we will continue using them. But now we have this new provider, Mapbox, instead of Digital Globe in the past, and you can request that, let's see if this works. This has to go through cloud because we count how many tiles you are downloading, and you have, I think it's about 10,000 per month. So we pay for that for you. And for higher zooms, we have the image coming directly from Mapbox without us having to specify it. Right? And that's a map of the area. That's an image, right? So notice that Mapbox requires that we add credits here. And the same thing will happen in geographics, right? So that's a map in geographics with satellite imagery and also this credit information. Okay. Obliqueness. So this is one of the aspects I was mentioning before, motivated mostly by Astro. In Astro, there are many coordinate systems, many frames related one to another by a spherical rotation. And so spherical rotations become very important, and we have to do fast spherical rotations of everything. So there is internal functionality to do this, and I'm going to show here for the Earth, but as geographics that not yet connect to this, it will do soon. So the idea is that if we have a polygon of the Earth, right, we might decide that the pole is somewhere else, right? And so we can do this type of rotation anywhere. Now the thing is that for what is needed in Astro is actually the information of the so-called graticules, the grids of longitudes and latitude lines, right? And so this is the type of thing that is actually needed there, right? So it's rotating these grids. We will see in a moment how many different grids of coordinates we have to use in Geo. Sorry, in Astro. We have had for a long time some projections doing this, like the oblique Mercator projection, which is able to do something like this, right? And so we see the same type of grid that this was showing, but this is done via the projection itself rather than an engine that does rotations in advance, which is what we want to do in the future. Okay, and to finalize in the last few minutes, this is the part of the talk which is actually more Astro than Geo, but that I'm going to explain here to have more time in the next talk. So the idea is that if we want to do precise computations, we have to have precise frames and coordinate systems. So it's always important to separate two parts in measurements: the physics part, the maths part. The physics part has different names in different areas. So in Geo, we refer to datums, right? In time, we refer to time systems, which is an option in the date object. And now in Astro, we are going to refer to frames, our reference frames. Then we have the maths. The maths in Geo are the projections. In time is the calendars. And in Astro is going to be the coordinate system, spherical, cylindrical, that type of thing. So again, we can only refer to very precise locations in space if we have precise frames. So the main difference between Astro and Geo is that in Astro, spherical geometry is enough. In Geo, we always need ellipsoidal geometry, which is a lot more complicated. However, in Astro, we have time, which is absolutely fundamental. Everything is moving in time, even with high speeds, so we will need relativity. In Geo, there is little time dependence. Now, tectonic drift is becoming important, but it's small, it's centimeters per year. Okay, so time systems were introduced recently, 2 cycles ago. And remember that they represent the physical way in which we measure time. And we have essentially 3 main ways. Using atomic clocks at the surface of the Earth. And these are the time systems related to that. We have the rotation of the Earth, which is irregular. There were many in the past, but now only one is used, which is called UT1. There were UT0 and UT2, etc. And then we can use time as measured in other places of the solar system. Gravity plays a role. So we can measure it at the center of the Earth, at the center of the solar system, etc. And this is a graph that is very important to show and the changes in time. So this is the drift between this type of time, the time determined by the rotation of the Earth and the atomic time and the atomic clocks. So this is the evolution of the drift, which is now about 70 seconds. And this is a curve, which is the orange curve is measured, and the blue curve inside is what we are trying to do to approximate it via leap seconds. And something very interesting is that even though on average the Earth is slowing down, recently it's speeding up. And so if this curve continues going down, it will happen in a few years that we will have to remove a leap second, something that has never happened before. That's quite interesting. Something that I will be using a lot in the Astro talk is J2000. J2000 is both a frame and a date. As a date, it means this date. And I'm going to use that opportunity to show this. So this is a date. We can describe it in the Julian year calendar. We can convert it into a normal year. And you see it's using TT, terrestrial time. This is one of the atomic clocks determining time systems. And now we convert it into UTC, which is our standard civil time system, and we get the actual time. So J2000 is a very, very precise instant in time, which is this one, right? And it has these 3 digits, no more digits. It's exactly defined by these numbers. And by the way, very quickly, in 13.2, we have a new function called random date that allows you to create random dates in different periods of time. That's very useful for testing and playing with times. Okay, very quickly, this is the final slide. So this is a collection of the very many frames that we will be using in Astro. So there are main 4 families. They depend on a choice of plane. We have here the ecliptic plane, the plane of the orbit of the Earth around the Sun, or of the Sun around the Earth. Then we have here the equator of the Earth. And these 2 planes are moving. So it's a bit of a mess to have a reference system that is based on these frames. So both of them have variants. And so when we say the equatorial frame or equatorial coordinates, one has to be careful about which one of these we are talking about. They are centered at different places. This means the solar system by center. Some do not move with respect to distant stars, which is something technologically very impressive, something that has only been possible to do in the last few decades. And they differ also in the choice of x-axis. And for example, some of them move with precession only, others with precession and nutation. Others always have the same XY plane, but the x-axis, XY axis are rotating with the Earth. And there is this one which also considers the fact that the instantaneous axis of rotation of the Earth is not well aligned with the geographic axis of the Earth. That's something called polar motion. So in order to have precise computations to arc seconds or even beta, we need to take all these things into account. The acronyms are pretty horrible. This is International Celestial Reference System. This is Celestial Intermediate Reference System. Same thing here. This is Geocentric Celestial Reference System. This is True Equinox, True Equator, True Equinox, Mean Equator, Mean Equinox. So I will use these from time to time, but the key idea is that we always have to remember that these are versions of the same frame, the equatorial frame of the past, but precisely aligned with the physics, so that we can use milli-arc-second measurements, etc. There are frames aligned with the ecliptic frame. Again, we can choose the x-axis, and we have the galactic plane too. And we have the horizontal plane, which is our local horizontal planes, right? So we are measuring things with respect to where we are. So here we need to know where we are in order to do this computation. Okay, so this is a fascinating area of physics and technology, to be able to describe all these different frames. And in computations that we will see in the next talk, you will be seeing some of this in action. Okay, so I think I have like 3 minutes or so for questions before I move to the next talk. Yes, we have this partially done. Now the GDAL library also offers alternatives to do that, and so that's going to be of help. But yes, you're talking about GeoServer protocols. Yes, WMS, WMTS, etc. Yes, yes, we need to complete that. Yeah, indeed. We have already an importer of GeoJSON. So if you do import, the export. Right. Yeah. So that's another thing that we probably gained from GDAL. Yes. Not this one yet, but it should come also via. I mean, GDAL has like 200 formats, so we were just experimenting at the beginning with adding these new ones. Yes.